Hey everyone, and welcome. I'm so excited you're joining me for this explainer. If you've ever debugged a test bench that just completely stalled out because components were stuck waiting on each other, you know exactly how incredibly frustrating that can be. Well, today, we're fixing that. We're tackling a really foundational concept in the Universal Verification Methodology, or UVM. We're going to talk about routing transaction data efficiently through your test bench using analysis ports. If you've ever wondered how a monitor tells a scoreboard exactly what's happening on a bus without slowing down the simulation at all, you are absolutely in the right place. We are going to track a transaction's entire journey.
Okay, let's dive right into this. Here is our agenda for today. First, the power of broadcasting. Second, the anatomy of analysis ports. Third, the monitor to scoreboard flow. Fourth, building the monitor. Fifth, implementing the subscriber. And finally, connecting the test bench. All right. Section 1, the power of broadcasting. We're looking at decoupling timing and execution.
So, at the very heart of UVM's modularity is transaction-level modeling, or TLM. TLM is essentially just a message passing system. But to avoid those painful stalled simulations we talked about, we need a way to pass messages that doesn't cause our simulation components to block or wait on each other. We need total decoupling between the timing of our bus and the execution of our checkers. Enter the analysis port. By definition, an analysis port is a specialized TLM port that relies on a single function, the write function. Its sole purpose is to publish read-only transactions to any number of listeners. And because it's read-only, listeners can't accidentally corrupt the original data. Actually, I want you to think of an analysis port literally like a giant radio broadcast tower. The tower transmits a signal out into the world. It doesn't know and frankly doesn't care at all if one radio is tuned in, if 1,000 radios are tuned in, or if nobody is listening. It just broadcasts.
Now, to make this work, we've got two distinct endpoints. First, the analysis ports. These are our publishers, and they're always depicted as diamonds in UVM architecture diagrams. Then we have the analysis exports, or IMPs. These are subscribers. They're the radios tuning into the broadcast, and they're depicted as circles. So the diamond sends and the circle receives. Simple as that.
Moving right along to Section 2, Anatomy of Analysis Ports. Let's explore the UVM base classes.
Now, what's really interesting about this slide is what's actually happening under the hood. It's beautifully simple. Looking at the class summary straight from the UVM manual, notice that under Methods, there is literally only one, the write method. When the component calls this, the port just cycles through a list of connected exports and calls their respective write methods.
But here is the most critical technical detail you need to take away from this entire explainer. That write method is a void function. Because it returns no value, the execution happens instantly, in zero simulation time. This means the call will always complete in the exact same delta cycle, regardless of how many massive scoreboards or super complex coverage collectors are connected to it. The broadcaster's execution thread is never blocked, which means your bus monitor never misses a single beat on the physical interface. This quote from the documentation perfectly summarizes why this methodology is so incredibly powerful. It says, an analysis port may be connected to 0, 1, or many analysis exports, but the operation of the component that writes to the analysis port does not depend on the number of exports connected. That is the ultimate form of plug-and-play modularity. You can add or remove checkers without ever touching your monitor code. Okay, Section 3, the monitor to scoreboard flow. Let's trace the transaction. Let's see this spatial and logical flow in action. It's really a three-step journey. Step 1, the monitor, sitting right inside our agent, passively observes the pin-level activity on the physical interface and packages all those raw wiggles into a nice, abstract transaction object. Step 2, the monitor calls the analysis port's write function, passing that transaction object as an argument. And instantly, Step 3, all connected components, like our UVM scoreboard, receive a pointer to that exact object through their implemented export.
Section 4, Building the Monitor. Let's look at instantiating the publisher.
All right, enough theory. Let's get our hands dirty and look at how we actually write this in SystemVerilog. First up, we declare the publisher. Inside our custom monitor class, which extends UVM_monitor, we declare a handle of type UVM_analysis port. Notice we parameterize it with our specific sequence item type. This is absolutely crucial because it strictly types the port so it can only broadcast this specific transaction type. That prevents nasty mismatch errors at compile time. Then, typically inside the component's build phase, we instantiate it by calling new, passing it a string name and the parent component.
Once the port is built, we use it during the run phase.
Inside a loop, where we're sampling the bus, we first create a new transaction object. Oh, and a quick pro tip for you, always make sure your new call is inside your loop so you create a fresh object every single time, instead of accidentally overwriting the old one. We then populate it with the sampled data, like setting the address. Finally, we broadcast it instantly by simply calling write on our port. Boom, the data's out there into the ether. It's not the monitor's problem anymore.
Next up, Section 5, Implementing the Subscriber, Receiving the Broadcast.
So the monitor has shouted the data into the void. How do we catch it? Well, this is the UVM_subscriber base class, and this brilliantly illustrates how UVM handles the receiving end. It has a built-in analysis_export, but look closely at the bottom under methods. It defines write as a pure virtual method. This means if you extend this class, UVM essentially forces you to write your own custom implementation of the write function. It's an enforced contract. If you want to subscribe to the data, you must define exactly what to do with it when it arrives.
Now, standard subscribers are great for single streams, but let's be real. Scoreboards usually need to compare expected data against actual data. That means receiving from at least 2 monitors. Because SystemVerilog doesn't let us have 2 functions with the exact same name and the same scope, we use a really clever UVM macro. This macro dynamically generates uniquely named ports behind the scenes for us. It allows us to declare suffixes like expected and actual, so we can implement uniquely named write functions right within a single scoreboard component. It's a lifesaver.
So the crucial point is how we write one of those functions. Notice the major safety measure here regarding the transaction copy. When the monitor calls write, it passes a pointer to the transaction object. Your very first step must be to deep clone the incoming transaction using the copy method. Think about it. If you just pass the handle around and another subscriber modifies the data, it corrupts the data for everyone else. You definitely don't want that. Therefore, the passed value must be treated as read-only. Once you have your own safe, deep-cloned local copy, you can pass it to your comparators or coverage groups without any worry.
And finally, Section 6, Connecting the Test Bench, tying it all together.
We have our monitor sending and our scoreboard ready to receive. This final step is the easiest part, but it's where the real magic happens. In your test environment's connect phase, which executes from the bottom up after everything is built, ensuring both endpoints actually exist in memory before we try to link them, you simply call the connect method on the monitor's analysis port, passing it the scoreboard's export as the argument. That single line establishes the permanent, zero-time communication link for the entire simulation.
Now you might be wondering, what if I have a component that actually needs to block? Say, a sequencer that needs to wait for a transaction before deciding what to do next. If the write function executes in 0 time, how does a blocking component keep up? Well, the answer is the UVM_TLM_analysis FIFO. By connecting our port to this specialized FIFO, it acts as a perfect unbounded buffer. The monitor writes to the FIFO instantly, and the consumer can pull transactions out of it at its own pace using blocking get calls. It completely bridges the gap between zero-time broadcasting and time-consuming execution.
And that brings us to the end of our transactions journey. We've seen how analysis ports allow us to broadcast data in 0 simulation time, completely decoupling our monitors from our scoreboards and coverage collectors. This means we can swap, upgrade, or remove checkers without ever breaking the core agent logic. So, I'll leave you with this. Now that you understand the sheer power of this plug-and-play architecture, how will you use this flexibility to design your next system-level test bench? Thank you